Hello students, in this lecture we are going to study continuity and uniform continuity, and actually we are starting the second unit of this paper, that is metric spaces. Continuity and uniform continuity. So you are studying the concept of continuity from 11th and 12th. We know that the basic definition of function f is said to be continuous at a point C if limit f of x extends to C is equal to f of C. So this is the definition of continuity in terms of limit form, that is the limit f of x extends to C is equal to f of C, then we say that the function f is continuous at a point C. We can write this definition in terms of epsilon and delta also, that is function f is said to be continuous at a point C if for epsilon greater than 0 there exists delta greater than 0 such that mod f of x minus f of C is less than epsilon whenever this 0 is less than mod x minus C, it is less than delta. So this is also definition of continuity in terms of epsilon delta. Mod f of x minus f of C is less than epsilon. Same meaning, that is limit f of x extends to C is equal to f of C. Now let us define the continuity in metric space. So how we define definition? So let x d1 and y d2 be two metric spaces. A function f from x to y is said to be continuous at a point A belongs to x if for epsilon greater than 0 there exists delta greater than 0 such that d2 of f of x f of E is less than epsilon whenever d1 of xa is less than delta. So this is the definition of continuity in metric space. That is, let x d1 and y d2 be two metric spaces, then a function f from x to y is said to be continuous at a point A belongs to capital X if for epsilon greater than 0 there exists delta greater than 0 such that d2 of f of x f of A. Here instead of mod f of x minus f of A, here we have written d2 of f of x f of A is less than epsilon whenever d1 of xa is less than delta, because here we see this is the mapping x to y. If we take this x belongs to capital X, then f of x belongs to this capital Y. And here d2, what is d2? D2 is the metric for metric space y d2, and d1 is the metric for metric space x d1, and therefore if we take x from capital X, then f of x will be, there is the image of that, and that belongs to y, and therefore we have written this d2 of f of x f of A less than epsilon whenever d1 of xa is less than delta. So this is the definition of continuity in metric space. Now let us prove one important theorem on this continuity. So there is one theorem. Let x d1 and y d2 be any two metric spaces. A function f from x to y is continuous at a point A belongs to capital X if and only if for every sequence an converging to E, we have limit f of xn n tends to infinity is equal to f of A. Or we can say that this sequence f of xn converges to f of A. Or in other words, we can write this sequence an converges to A implies this sequence f of an, this converges to this f of A. So this we have to show. So in this theorem, it is given that the xd1 and yd2 be two metric spaces and there is one function f from x to y. We have to show that a function f is continuous at a point A belongs to capital X if and only if for every sequence an converging to A, we have limit f of xn n tends to infinity is equal to f of A. So there is a word if and only if. All of you know that its meaning. It means in this theorem we have to prove both statement and its converse. So in the first part, suppose we have supposed that a function f from x to y is continuous at a point A belongs to capital X. Then what we have to prove? Then we have to prove that for given sequence an converging to A, we have this limit f of xn n tends to infinity is equal to f of A. And on the other side, again we have to suppose this, and we have to prove that f is continuous at a point A. So this is the statement of this theorem. So let us prove this. So proof for this. Proof. First let us suppose that f is continuous at a point this A belongs to this capital X. And of course we are considering two metric spaces, that is xd1 and yd2. So f is continuous at a point A belongs to capital X. We have seen earlier the definition of continuity in this metric space. So by using that definition, now one more thing we have to assume here. First let us suppose that f is continuous at a point A belongs to capital X and let an be a sequence in capital X such that this an converges to A, or that is limit an n tends to infinity is equal to. This also we have to suppose here. An tends to that is. Now here it is given that if we have supposed that f is continuous at a point A belongs to capital X, and therefore by using the definition of continuity for epsilon greater than 0, there exists delta greater than 0 such that d2 of f of x, f of A is less than epsilon whenever this d1 of xa is less than delta, and this is our argument number 1. This is our argument number 1. This is our argument number 1. Now, one more thing we have supposed, that is, we have supposed that there is a sequence an converges to A, and therefore, as this sequence an this converges to A, so which implies that for epsilon greater than 0, there exists a positive integer n0 such that d1 of xa is less than delta, and for all n this is greater than or equal to m. For all n greater than or equal to m. Now putting x is equal to an in our argument 1, what will happen? See, this is argument 1, and here we are putting x is equal to an. So what will happen? That is d2 of f of xn, f of a is less than epsilon whenever d1 of xn a is less than delta for all n is greater than or equal to m. And what does this imply? Which implies that this sequence f of an, this converges to f of a, or in other words we can say that this limit f of xn and tends to infinity is equal to this f of a. So this proves the first part of the theorem. Now what we have to prove? See, now what we have to prove? We have to prove that limit f of xn and tends to infinity is equal to f of a if, and then what we have to show that then f is continuous at a. Then we have to prove that continuous at a. But now here we will give proof for this in some other manner. So here we will suppose that f is not continuous at a. And as we are supposing that f is not continuous at a, then what we have to show? Then we have to show that this sequence f of xn does not converge to f of a even though there is a sequence an this converges to e. By taking negation we are proving this. So let us suppose that f is not continuous at a. So f is not continuous at a means what happens? By definition, for epsilon greater than 0 there exists delta greater than 0 such that d2 of f of x f of a is greater than or equal to epsilon if d1 of xa is less than delta, greater than or equal to, because we are supposing that f is not continuous at a, and therefore this d2 of f of x f of a is greater than or equal to epsilon if d1 of xa is less than delta, and for some this x belongs to this capital X. Now by taking delta is equal to 1 by n, see, by taking delta is equal to 1 by n, we will get one sequence. Delta is equal to 1 by n means suppose 1, d1 of x is less than 1, suppose 1 by 1, d1 of x is less than 1 by 2, 1 by 3, 1 by 4. So by taking delta is equal to 1 by n, we get one sequence such that f of xn, f of a is greater than or equal to epsilon, and if this d1 of a and e is less than 1 by n, and thus here this f of xn does not converge to this f of x. So in this way we have proved this part. So this completes the proof for this theorem. So here we stop.